Alright, so we're at the next video for our screencast for Math 1410 Linear Algebra, and at this point we are actually ready to say how to write down a complex number in polar coordinates. So in the previous video we introduced these various parts of a complex number. So we said, okay, if I have a complex number, say z equal to x plus I, y, we said, well, we can define r, known as the modulus of z, simply as the square root of x squared plus y squared. That's the r value for our polar coordinates, and we define an angle theta via the relationship tan theta is equal to y over x. You do have to be a little bit careful with the angle to make sure that you define an angle that places you in the correct quadrant. And if you're working on the online homework problems, once you get to the online homework problems having to do with complex numbers in polar coordinates, one of the things that you're going to have to watch out for is some of the problems are going to specify that the angle has to land in a particular interval because the computer is pretty good at evaluating certain things, but one of the things it doesn't seem to be all that good at is accepting different angles that differ by, say, multiples of 2 pi, and so they will specify a particular interval, and that occasionally can cause a little bit of trouble, but we'll deal with that when we come to it. Okay, so as I mentioned, we have the modulus of the complex number written here. We have the argument theta, which satisfies this relationship. Tan theta is equal to y over x. And if you think about using the polar coordinate conversions that we dealt with a couple of videos ago, this tells us that we can write x and y in terms of these values, in terms of the modulus of z and in terms of cos theta. So usually we will set, r equal to the modulus of z, as you see down here, and that means that you can write this as r cos theta, you can write this as r sine theta, and that means overall your complex number can be written in this form here, right? So you've introduced the polar coordinates, but you really are technically still writing this thing in rectangular form. You're still writing it in the form x plus iy. You've just expressed x and y in a different way, right? Because you still have a number plus I times another number, so we haven't really gotten out of rectangular form yet. Now, you do have to, like I mentioned, you have to watch out a little bit with the value of theta. Most of we may require, for example, theta to be between minus pi and plus pi. Usually it's kind of convenient for fourth quadrant angles to just, instead of writing something like 11 pi over 6, it's usually more convenient to just say minus pi over 6. It's a nicer angle to work with. You may, if you want to, though, you could work with angles between 0 and 2 pi, and of course, you don't have to stop there. You could work, with angles between pi and 3 pi, or there's lots of things you can do, but minus pi to pi is a pretty common choice, and it's the one that we will go with. Okay, so how do you actually kind of get this into a useful form where you can work with it? The keystone to this is what's called Eulers Formula. So Euler's formula is really quite remarkable. It's this guy here. Euler's formula says that if you take a complex number of this form cos theta plus I sine theta, so this would be the case here. This would mean you're dealing with if this is a complex number z, you're dealing with a case where the modulus of z is equal to 1. And if you go back to the previous slide and kind of think about things for a bit, you realize that in fact every complex number with modulus 1 can be written in this form for some angle theta. So instead of writing cos theta plus I sine theta, we write e to the I theta. We write this exponential. And this seems kind of like it comes out of nowhere. It doesn't seem like there's any kind of good motivation for it. If you study complex function theory, you'll see that actually there are a number of ways to kind of understand this that all make sense, but most of them require a little bit more calculus background than we are going to assume for students in 1410. In fact, I'm not going to assume that you know any calculus. So some of the explanations as to why this is a reasonable definition are going to have to wait for future courses if you really are interested in them. And some people, because this idea that you use an exponential, it does seem a little bit unmotivated. It seems a little bit odd. One of the things that you will find, and our textbook is no different, is instead of writing e to the I theta, you will often find this notation CIS of theta, which is somehow supposed to remind you of a trig function, right, like cosine or something. But the CIS here, you might be able to guess what it stands for. It stands for cosine I being, well, the square root of -1, and sine being sine. So it's this idea that you're doing cos plus I sine is what the CIS stands for. So some people will just write it as CIS theta. Use whichever notation you prefer. Either one is acceptable. The exponential notation has the advantage of being kind of easier to remember in terms of its properties. And then one of the reasons why this exponential notation makes sense is that if you kind of play around with trig identities, and I went through one of them here, you can ask, well, what happens if you kind of, put a sum in there? What happens if you have alpha plus beta? You've got two angles, right? So I'm going to look at e to the I times alpha plus beta. And so you take the definition up here, the one with the green box around it, and you plug in alpha plus beta. And you either remember or you look up the summation identities for sine and cosine, and you write those out, and you do some playing around, and you simplify, and you realize that, in fact, e to the I times alpha plus beta, and if you want to think of that as e to the I alpha plus I beta, right? You could push the I through the brackets. Is equal to e to the I alpha times e to the I beta. And if you think in terms of laws of exponents, remember that if you're dealing with real exponents, if you have something like e to the x plus y, one of your laws of exponents says that e to the x plus y is the same thing as e to the x times e to the y. And so this kind of, these several lines here, there's several lines of working with these trig identities, and this algebra tells you that this law of exponents works if instead of dealing with real numbers, you're dealing with purely imaginary numbers. So if you put I in front of both the x and the y, this is an identity which still holds. Another result, and it's one that we don't have the ability to prove in this course, well, at least the rigorous method of proof uses a technique called mathematical induction that you would encounter in a course like Math 2000. Says that if I take e to the I theta and I want to raise it to a power, that's the same thing as just multiplying theta by that power. So e to the I theta raised to the power of n, this guy over here, is equal to e to the I n theta. And again, this should remind you of another one of the laws for exponents, which says that if I take e to the x and I raise it to the power of y, that's the same thing as e to the x times y, right? And so again, the laws of exponents seem to work when you have this complex number, this square root of -1 sitting up there in the exponent. And if you take a course in complex variables, you'll learn that in fact the laws of exponents hold for the exponential function when theta could be any complex number, n could be any complex number. Here I'm assuming that theta is an angle, it's a real number. I'm assuming that n is an integer, but it doesn't have to be an integer. It could be any complex number. And so things actually work in general here. The laws of exponents work in general. And because of that, it means that you can just manipulate these complex exponentials the way you expect to be able to manipulate them. That's the advantage over using the CIS notation, because with the CIS notation, you just got to remember certain rules. You'd have to remember that CIS of alpha plus beta is equal to CIS of alpha times CIS of beta, and it's easier to remember if you write it down in terms of kind of properties that you're already familiar with. Okay. So this result, this De Moivre's theorem, sort of tells you how to deal with powers of well, at least powers of complex numbers that have length 1. It says, oh, you can just, you take a complex number of length 1, figure out what angle theta it corresponds to, and if I want to raise that to a power, I just have to multiply the angle by theta. And that's really convenient because, if you think about computing powers of complex numbers, if I wanted to kind of compute this guy here, I would be multiplying cos theta plus I sine theta. I'd be multiplying by itself some number of times. Maybe want to raise it to like the 5th power or something, right? You want to do that. Raising that to the 5th power and multiplying everything out, that's gonna take forever. On the other hand, multiplying theta by 5, that's a piece of cake. So that's this is a really nice result, and it's quite powerful. Okay. So once you've introduced this notation, this is one way of kind of, getting out of this x plus iy form, writing things as exponents. And then, of course, you want to be able to convert back and forth. So if I wanted to, if somebody handed me e to the I pi over 4, and I wanted to put that back into the form of a complex number that I'm familiar with, well, I would say, okay, by definition, this is cos pi over 4 plus I sine pi over 4. And so that is 1 over root 2 plus I times 1 over root 2. E to the I pi over 2, that would be cosine of pi over 2 plus I sine of pi over 2. And we remember that cos pi over 2 is 0, sine of pi over 2 is 1, and so we simply get I, right? Again, that's one that's kind of easy to visualize if you think of points on the unit circle, right? I is sitting up here at an angle of pi over 2. So that one makes sense, right? That one makes perfect sense. Geometrically, this should make a lot of sense. E to the I pi. E to the I pi, this is a result that a lot of people find quite fascinating, because what do you get? You get cos pi plus I sine pi. Cosine of pi is equal to minus 1. Sine of pi is equal to 0. So this is just equal to minus 1. And so some people might write this as, the way they might like to write this as, is they might like to say, okay, e to the I pi plus 1 is equal to 0. Right? The physicist Richard Feynman, this was his favorite equation of all time, and I think it's a favorite equation of a lot of people. Because if you think about what's in there, right? I mean, you have some of the most fundamental constants show up in this equation. You have 0, which is the additive identity. You have 1, which is the multiplicative identity. You have pi and e, which are among the most famous of the irrational numbers, of the so-called transcendental numbers, things that can't even be written down as square roots. You have I, the square root of minus 1. You have, of all the sort of numbers, fundamental numbers that you encounter in life, these are 5 of the most fundamental ones, and somehow they all fit together into one equation, which, somehow is fairly satisfying. This last one, I'll leave that one as an exercise for you guys to look at. See if you can try that one out. Again, it's simply a matter of evaluating the sine and the cosine functions. The other one here, how do we show that these complex exponentials are somehow periodic? Adding multiples of 2 pi don't matter. Well, adding a multiple of 2 pi doesn't matter because it doesn't matter when you do it to a sine and cosine function, right? So e to the I theta, phi to theta plus 2 pi k. That's equal to cosine of theta plus 2 pi k plus I sine of theta plus 2 pi k, right? But the sine and cosine functions are periodic. They have this property that adding multiples of 2 pi doesn't change them, right? Because that corresponds to a full revolution, and going all the way around the circle takes you back to where you started. So that's the same thing as cos theta plus I sine theta, which is e to the I theta. Okay. Now let's come back to kind of complex numbers in general, right? Ones that don't lie on the unit circle. How do you kind of put everything together? Well, we can take z, and we know from the previous, like the second slide, that we can write z as the modulus of z times cos theta plus I times the modulus times sine theta, right? We know that we can do this, right? Using the fact that x is equal to r cos theta, y is equal to r sine theta, and with r equal to the modulus of z. Now, of course, this guy here is a common factor. You can take it out. So you pull out that r, the modulus of z, and you have cos theta plus I sine theta, right? But then Euler's formula tells us that cos theta plus I sine theta, that's e to the I theta, and so we get this this nice compact form, right? So z equals r e to the I theta. So this is the polar form of our complex number. Now, one of the things that's kind of nice about the polar form, if I have two complex numbers, so let's say I have z is equal to r e to the I theta, and I have w is equal to I don't know, let's say s e to the I phi. Okay, I've got two different modulus values, two different argument values. I've got two different complex numbers. Now, you could plot those guys. So maybe z is here, and maybe w is here. Let's make w a little closer to the origin here. Okay, so we can draw these line segments. By the way, addition can also be kind of understood geometrically in terms of vector addition, this sort of tip to tail or parallelogram rule. We'll talk about that when we talk about vectors. If you draw a little parallelogram, if you think of those two sides as two of the four sides of a parallelogram, this point over here corresponds to the sum, w plus z. Now, what about the product? So the arguments here, we have our two arguments. We've got our theta here, we've got our phi here, and if you multiply z and w in sort of the most naive way, and there is some proof that's required here, you've got to kind of work through the properties for both the modulus and the argument. But we've done some of this already, and you can work out that you just you rearrange this the way you expect to be able to rearrange. Sorry, that should be an S, and it works out the way it should. So you kind of say, well, I should put the r and the s together. I should put the angles together. So let's write this as r times s, and then e to the I theta times e to the I phi, and we just proved that laws of exponents work the way we expect them to here. So this is r times s, and then e to the I theta plus phi. So if I'm taking a complex number w and I want to multiply by a complex number z, what happens when I multiply by z? Well, the argument gets or the modulus rather gets stretched by a factor of r, and the argument gets added. So we sort of, when we multiply by z, we stretch and we rotate, and so the result is going to be, well, I take my angle of theta and I add it on, and I'm probably going to end up somewhere maybe over here, right? So the z times w is over here, with my angle being theta plus phi, and this distance, the distance from the origin, is given by the product r times s. So there's a stretch factor that comes into place there. Okay, so that's the polar form of a complex number, and in the next screencast we're going to show how to put it to use.